cast a rational as a bool, I'm going to get true. What is true going to mean?
So now zero.
Not zero. Really? Is that useful?
Since it's no return type is mentioned as down declaration.
The return type is the operator type.
Oh.
So the return type is double return. No, you might say,
So
hey,
can
can anybody think of a reason for this one? Yeah.
Can you return another type?
No.
No. Oh,
No, because by definition you're returning this. That's the format. Okay. Does anybody, can you think of a good idea why how that could be useful? I could write this code. Okay, suppose I have a rational object called R. Here's the code. If R, do something. What does that mean? If R is true. It's true if it's non-zero. See what I'm saying? So now I can use a rational object in a condition. I can say if R not equal to true, while R equal true, do something, put a next R, read the next R, etc. So I can use this in a control statement. Okay, you're not impressed. It's good stuff. All right. Casting operators also explain certain types of codes that we have. And I think I already mentioned this at the very, very beginning of the semester, but you had no idea what I was talking about, which is fine. Some of you still don't have any idea what I'm talking about. But that's all right. That's what makes it interesting. Okay, so look at this. Float x3, y3, z3. So what am I creating? Right. So I'm going to say for int I equal to 0, cin into x sub I plus plus, cin into y sub I into z sub I. Okay. Do you fully understand this code? Is that clear, or is that clear as mud? Not clear? It's not clear, right? That's what I was hoping you were going to say. So the first thing that stops us a little bit is the cin into xi. Because that's in the second part of the for loop control, which means it looks like a condition. Okay? First of all, everybody knows what cin into xi does, right? It's going to read a floating value from the keyboard, right? From standard input. Or from a file if I do IO redirection at the command line, right? So, I'm going to read it. And tell me, what is this middle piece of code going to return? Well, no. It's going to return an iStream reference.
Yeah, the host.
iStream reference. So now, but iStream reference is not going to help us. So the iStream class has a casting operator, which casts it to bool. Therefore, it's equal to true if it's been successful. So there's an interpretation. Cin into x sub I. So if so you say, but I don't see any casting operator. I know you don't. But this is being used as a condition. So therefore, it's now going to test whether this is 0 or non-zero. So it has to return either non-zero for true, or 0, which means it's false, or literally false. Because false, you ever see false before in C++? F-A-L-S-E? No? How many people have seen false?
Zero.
False. F-A. Well, okay. You know how they do it? Pound define false. 0. It's a secret number, right? That's all it is. It's just a number. It's just a 0. But it looks great. Like false. Wow, this language is so robust. Just pound define false 0 in parentheses. Maybe we give it a cast as a void pointer or something like that. Just that's all it is. All right. So that's how that works. So suppose that an error is set to not equal to 0 on the error operation to stream. So basically, if we are successful in, so basically, if I type ABC, this operation will fail. And therefore, what's going to happen? The flag's vector will get a 1 in it. Remember, fail? And so what's going to happen is, because this is being used as a condition, then C++ will implicitly, that means on its own without being asked, implicitly, it will cast this. And the cast probably returns by masking out whether that bit in fail is set to true. And so that's how you do it. So example, so basically C into N, so that could fail. Therefore, the stream casting operator will return appropriate values for true or false. For example, so here's the bool cast of output stream. If error equals 0, return true, else return false. See the false and true and false? They look very convincing. You see bool? You know what that is? That could just be a pound defined. See, everything you were taught to believe. Now you don't believe it so much anymore. It's like, everything could be a macro. Curse you. You know, IO stream, header file. You've been fooling me all these times. You know, true, false. Come on, really. What if you want to have uppercase bool? Well, you could define your own. Pound define bool, big, little bool. You can use big bool. Nobody else can, but you can. All right, so that's good. All right, this is not so important, but I'm going to show you a little bit about it. We talked a lot about functional parameters and void changes and all that kind of good stuff. So basically, what I'm going to show you is just the basic logic of how you would implement a real algorithm using a generic approach to functional pointers and void pointers. So essentially, what the idea is that I want to be able to quicksort any kind of data. I don't want to have to write this quicksort algorithm over and over again because it works very well for me. I'm done with it. So I create it, and I have quicksort here. And so the first thing I have, the first parameter is any is a pointer to void. But of course, you know, a pointer to void can be anything. So really what I'm expecting is I'm expecting a pointer to any specific type. And I'm going to cast it as a void. That way I can capture double pointers, int pointers, char pointers, rational pointers, whatever I want. So I'm casting basically this as a void, so I can do that. So then in the quicksort, I'm going to have the left index, which I need for quicksorting. I'm going to need the right index for quicksorting. But then, because the array is coming in as a void, I have to supply functions that know how to operate on the specific type I am actually operating on. So for example, if I send in an array of int, so therefore any becomes, in reality, it's really an int pointer, even though it's cast as a void pointer, but we know it's an int pointer. So therefore, I will supply functions, compare function and swap functions, that will know how to compare specifically the int elements. If any is coming in, it's a rational array or a pointer to rational, then I will supply specific functions that operate on rationals, compare them and swap them. Again, the functions are assuming that functions operate on a specific type, but the array is generic. So once those functions come in, they know that they're operating on rational, so this must be rational. If the function is operating on int, they know this is going to be an int. Okay, so here I just have what? I created a nice type def. And again, this looks complicated, but you know it's not that hard. All it is basically is, again, hide the type def. So basically CMPFN is a pointer to a function that takes an array, 2 ints, and returns an int. That's all it is. It's a type. So CMPFN, compare function, CMPFN. Swap FN, swap function. So I'm basically comparing these and swapping. So this allows me to pass in a function very simply with a type and another function very simply with another type. And so you'll see what it looks like. So I'm not going to go through the code of Quicksort. I mean, you can do that on your own. It's not that complicated at all. But the bottom line is this. We have two indexes on an array, and basically we usually take the first element as a pivot element, and anything smaller or less than or equal to that, we move this here. Anything bigger than that, we move this here. If we ever stop, that means this is not less than or equal to, this is not greater than, so if we exchange them, we break both those problems. And we keep the I going up, the J going down, and until they cross each other. When they do cross each other, then I have essentially partitioned less than or equal to the pivot and greater than the pivot, which means the pivot, which is still here, boom, is placed in there. That's the idea. So I'm not going to, and it's recursive and all that kind of stuff. So basically what we have here is, here we're trying to move I to the right, here we're trying to move J to the left. So now, notice that the partition, which is the big logic behind Quicksort, what we're going to do is we're going to say while, now we have CMP, any, I, R. So what is R? R is my left and my right. And I is going to be the left. J is going to be the right. So I'm comparing in this array element sub I against element sub R. And basically, the CMP function, I'm going to return a value less than or equal to 0. And if that's the case, then what happens? That's a condition less than or equal to 0. That's a condition for moving to the right. So I'm going to have this function return something appropriate. You know what's appropriate? Like the difference between two ints, the difference between two doubles, or maybe something with rationals. So basically, the CMP function. So this function, if it returns less than or equal to 0, and I is still to the left of J, then just keep moving I forward. Move forward. That means you're partitioning nicely of this less than or equal to. When you stop, and you try to move this one down, and you're trying to check if J is greater than I, and also if the compare function is returning greater than or equal to 0. If that's the case, then move J closer to I. When you stop, you're going to check if I and J are still, did not cross each other, they're still away from each other, then swap from this array element I++ with element J. I++ means I and J, really, and then I++ goes later. And finally, and I just do that for a while, finally, if I is not equal to R and this element is not equal to the right element, then we swap the initial element I, which is the first element, into the proper location, etc. And so Quicksort is basically, that's what it does. So this is my call to Quicksort. So I get a general array, specific functions. General array, specific functions for that type. And then I call partition, and partition has to basically do the partitioning. Once you decide where the pivot goes, if the pivot goes here, then now you have to recurse with this half, left to right, and with this piece, left to right. And that's what the recursion is all about. Quicksort to the left of the pivot, quicksort to the right of the pivot. Where's the pivot? The pivot is partitioned into K, and then we recursively sort left and sort right. Notice that the call to Quicksort gets the generic array and the two specific functions. When we call partition, we simply pass that generic array, and we pass those specific functions, because actually, it's partition that needs those. But people who don't know about how Quicksort works, they don't even know about partition. They don't care. But partition is the one that does actually all the work. All that Quicksort does is basically call partition, and then recursively solve the problem further. Questions? So as an example, you can see here is I'm creating a method like CMP int bigger, CMP int smaller. It's so easy, it's almost too easy, right? So you can see the CMP function fits into the prototype of the CMP-FN because it has void pointer int, returns an int. So it's a perfect prototype match. Same thing here in smaller. So all it does is basically, once you have an array, it will just take xi minus xj. Very simple. And here, xj minus xi for compare smaller. So one will help move I to the right, one will help j move to the left. And so you can see here I have an array of ints, 5, 3, negative 1, 9, 22, 99. Notice that d is equal to size of a over size of int. Does that make sense? What's d? What's size of a over size of int? That's the number of elements in the array, actually, right? I can do size of a because I am in the same scope where it was defined. That's why size of a will give me this times 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So it'll give me a 24 if it's a 4-byte int. So here, notice that I'm having the array. This is the first index, 0. Last index is d minus 1, because remember we always index from 0 to less than 1 less. And I do a compare bigger function. So I'm taking this function and I'm casting it as a CMP-FN. And I'm taking the int switch. Here I'm calling CMP int smaller, and I'm calling int switch. So what's going on here? Well, what's going on here is basically I'm sorting in ascending order, and here I'm sorting in descending order, because I'm giving you differently behaving compare functions. Swap functions the same. Now here is, I can use the same function, and this, what I'm gonna do is I'm gonna use rational compare function. So compare rational vigor, again, fits nicely, CMP-FN prototype, and swap FN, switch FN, or whatever it's called, swap FN prototype here. Generic function, int returns an int. Everything is the same. The only thing I'm gonna do here is look carefully what I'm doing in a red circle. Can you tell me what I'm doing? Anybody? Well, what am I doing? What technique am I employing here? How am I, what is this? This is actually utilizing the casting operator. Remember the casting operator? So basically what it does, it takes this x sub I and creates a double out of it by taking the top and the bottom, doing a quotient, which is a double. So I'm just doing a difference of the double quotients using a double casting operator. If this minus this is greater than 0, return 1. Else if it's less than 0, return -1, else return 0. Okay, that's it. So the casting operator is very useful here. I can use it nicely. The reason I have to do all this craziness is because I have to return an int. If I can return a double, I just do minus. Just like with the ints. But the ints minus an int is an int. But a double minus a double, if I cast it as an int, I could lose a value. Because if I'm in between 0 and 1, I get 0, not so good. Okay, get the idea? So here I am creating the same type of thing. And so now I'm going to sort. This is an array of rationals. Same code, size of rational going into size of B. That tells you how many you have, which is D. Same thing. Quicksort B 0, D minus 1. Reinterpret as CMP-FN. Compare rational bigger. Here's a switch. Compare rational smaller. Switch. And it works very nicely. And here it is.
So what is the priority of the casting operator?
Well, that's right. You can see that it's going to be, well, first of all, the bracket is more important. Why? Because the bracket is called a primary operator. So the primary operators, if you remember the order operation we talked before, you have, for example, this, the pointer is a very high priority operator. The bracket is a priority operator. So the primary operators. So they're going to come in first. And the reason you're asking that question, I bet, is because you saw this right here, where this is the cast, and this, so this is the primer, so it's going to get x sub I, then cast it. If you weren't sure, you would have to parenthesize from here to here, from here to here.
Because I asked because if we have a double cast operator for the rational class, okay, so we could have directly write xi minus xj, but so there is the minus.
If we had what is again,
xi minus xj directly.
xi minus xj.
And we have a double cast operator in the rational class and overloaded operator for minus.
Yeah, but that's a bad idea because then your subtraction of rationals will give you an int, and that's not consistent with the way we want to have the minus operator.
No, but if so it's like xi minus xj. Okay, we have a minus overloaded operator. Okay.
What does it return? What kind of
int,
return?
it will return int.
I don't like it.
For the rational.
I don't like it.
Okay.
No, because if you're going to return, if you have two, rational minus rational should be rational.
Rational, sorry. Okay, rational. And if we have a double casting operator, so which will be first, minus operator or the cast operator?
Cast operator.
Cast operator. So if
Because the minus is just a much lower, right? It's a binary arithmetic operator.
so if you have both overload operator for casting and for minus also, then xi minus xj greater than 0 will work.
The rule is this. It's not even a complicated rule. The rule is look at the old book. Oh, I found a great book. Because the Bible of C is a book. I told you about this book. It's about this thick, right? And I found that you can get it like online on PDF for free. It's a K&R C book, the best. And the reason I'm talking about that one is because with respect to this, I mean, C can't address overloading operators. It doesn't overload operating in C++ does. Basically, if there's a question, like what's gonna happen first, the answer is whatever would happen in normal C++ if it wasn't overloaded. I mean, the double cast exists and the minus exists. Whatever is minus and casting with ints, the same thing over here. Because that's the job of the parser. So the parsing of the code is always the same, regardless of how it's being used or overloaded. The parser is the parser. That's why it's such an easy question for me. But I understand why it's a question. But now you understand, so there's not even a question.
Okay.
Yep. Okay, so that's that. This is too boring. Okay, I'm not gonna go through that. It's a very good piece of notes, but I'm just not gonna kill you guys with this. Okay. All right, now we're coming to inheritance again. Okay, inheritance is a very powerful tool in C++, more powerful than most languages, but also has more, I guess we're done.
Yeah.
Are we out of time?
Done.
Okay, well, I guess we're finished for the day. So I get too excited. So we're gonna start over here. We're gonna start, I know we've been moving kind of quick, but we're gonna probably pick up the pace a little bit. Because we gotta cover a lot more material. But we're doing well, and I think the most important thing is that you learn what you learn very well, as opposed to just learn everything, but not very deeply. So that's my goal.